Hello, chemistry explorers. Did you know that turning something as stinky as a nitro compound into a useful amine is like turning a pumpkin into a carriage? Let's dive into how nitro compounds are transformed into primary amines, the vital ingredients behind dyes and medicines. Nitro compounds undergo reduction, which is a fancy way of saying they gain electrons, to form primary amines. To achieve this, chemists use reducing agents like hydrogen gas with nickel catalyst, or metals like tin or iron in acidic conditions. Imagine a powerful team of electron providers working hard to make this happen. But here's a catch. Aliphatic nitro compounds, those with straight or branched carbon chains, and aromatic ones, which include ring structures like benzene, don't always behave the same way, and their yields and purity can differ. For example, when nitrobenzene, a classic aromatic nitro compound, is treated with tin and hydrochloric acid, it neatly converts into aniline, a primary aromatic amine, which you can think of as the star player in many dye and drug syntheses. Picture a reaction scheme in front of you, nitrobenzene on the left, arrows showing the reagents tin and hydrochloric acid, and on the right, aniline. This transformation is critical because aniline's derivatives color many fabrics and serve as building blocks for medicines. So, reducing nitro compounds isn't just lab magic, it's a cornerstone of industries that color our world and heal our bodies. Welcome back, future chemists. Imagine you want to stretch out a carbon chain but keep it intact while turning it into an amine. That's where nitriles and amides come to the rescue. Nitriles, which have a carbon triple bonded to nitrogen group, can be reduced to primary amines by using lithium aluminium hydride or catalytic hydrogenation. The reaction basically adds hydrogen atoms to the nitrilae, converting that triple bond into a carbon bonded to a primary amine group. Think of it as giving the nitrilae a makeover from RCN to a CH to NH2, where R is any alkyl group. Similarly, amides, which have a carbon double bonded to oxygen and single bonded to nitrogen, can also be reduced with metal hydrides. This process removes the oxygen and forms a primary amine, maintaining the original carbon skeleton intact. So, our Cong2 turns into a CH to NH2, keeping the molecular chain length the same. Why does this matter? Because it lets chemists build longer or more complex amines without losing parts of the molecule, perfect when making straight-chain amines used as building blocks in organic synthesis. Picture two neat reaction schemes side by side, one showing a nitrilae reducing to an amine, the other an amide doing the same, with reagents like lithium aluminium hydride and arrows showing hydrogen addition. These transformations give chemists control to design precise molecules for all kinds of applications. Hello, mechanism detectives. Let's zoom in on how nitrorenes, which are nitro groups attached to aromatic rings, get reduced step by step into amines. Imagine the reduction as a relay race where electrons and protons baton pass through different intermediate compounds. First, the nitro group converts into a nitroso compound, then to hydroxylamine, and finally to the aromatic amine. Each stage involves the transfer of 2 electrons along with protonation, adding hydrogen ions at just the right spots. Aromatic nitro compound, ARNO2, is first reduced to ARNO, then further to ARNHOH, and finally to ARNH2. Here, Ar represents the aromatic ring. Visualize a flowchart showing each intermediate with arrows and labels indicating electron and proton transfers so you can follow the molecular journey. Why does understanding this stepwise process help? Because it allows chemists to fine-tune reaction conditions, temperature, pressure, or catalyst to stop at intermediates when needed, which is very useful in producing specialized fine chemicals. So, this is chemistry's version of a molecular relay race that makes complex synthesis both efficient and selective. Greetings, Curious minds. Ever wanted to make a primary amine without accidentally creating messy secondary or tertiary amines? That's the magic of Gabriel's synthesis. This method uses potassium phthalimide, which is like a clever trap for alkyl halides. When a primary alkyl halide, think of Rx where X is a halogen like chlorine or bromine, reacts with potassium phthalimide, it undergoes nucleophilic substitution, kicking out the halogen and bonding to the phthalimide part. Then, by carefully hydrolyzing this intermediate with sodium hydroxide and water, the phthalimide group breaks away, releasing the pure primary amine NH2. Imagine the reaction scheme. First, Rx plus potassium phthalimide forms RPHD, and then hydrolysis with sodium hydroxide and water converts it into our NH2. Why is this method preferred? Because it selectively produces only primary amines, avoiding the headache of secondary or tertiary amine side products, making it a favorite in synthetic organic chemistry, especially when you want pure aliphatic primary amines for further chemical adventures. Think of it as the VIP express lane to primary amines. Hey there, molecular remodelers! Sometimes, chemists need to shorten a carbon chain while turning an amide into an amine, and the Hoffmann bromamide reaction is perfect for that job. Here, a primary amide reacts with bromine and an alkaline like sodium hydroxide to form a primary amine that has one less carbon than the starting material. For example, our conc treated with bromine and sodium hydroxide yields a NH2, losing the co part as carbon dioxide or carbonate. Now, this reaction involves a neat rearrangement step where an isocyanate intermediate forms transiently before water breaks it down to the amine. Picture a stepwise reaction showing the amide, bromine, and alkali combining, forming the isocyanate intermediate, and finally hydrolyzing to release the amine and carbonate species. This method is especially useful when you want to trim down a molecule's carbon skeleton or remove troublesome acyl groups during synthesis. It's like molecular scissors that snip off one carbon with precision. Welcome back, organic storytellers. Beyond nitro groups and amides, amines and oximes are versatile intermediates that can be gently coaxed into amines. Amines, also known as Schiff bases, have a carbon-nitrogen double bond, while oximes have a similar structure with an additional oxygen attached to nitrogen. Upon mild reduction, for instance, hydrogen gas with nickel catalyst for amines or zinc with hydrochloric acid for oximes, they convert into amines. Specifically, when an amine, written as a CH double bond NH, is reduced, it converts into a CH to NH2, which is a primary amine. Similarly, an oxime, written as a CH double bond NOH, also undergoes reduction to form the same product, RCH to NH2. This shows that both amines and oximes, on reduction, lead to the formation of primary amines. Imagine two reaction paths side by side, one from amine to amine using hydrogen and nickel, and the other from oxime to amine using zinc and hydrochloric acid, each labeled with reagents. These reductions are invaluable in synthesizing heterocyclic compounds and fine pharmaceuticals where precise amine groups are essential. So, amines and oximes serve as gentle chemical stepping stones to amines without harsh conditions. Time for a quick brain workout. Suppose you want to convert acetamide into ethylamine using the Hoffmann bromamide reaction. The given equation says acetamide, which is CH3CONH2, reacts with bromine and sodium hydroxide to yield ethylamine, CH3CH2NH2. Step 1 of the balanced reaction is acetamide plus bromine plus 4 sodium hydroxide molecules produce ethylamine, sodium carbonate, sodium bromide, and water. Notice the molar ratio is 1:1, meaning if you start with 0.1 mole of acetamide, you can theoretically get about 0.1 mole of ethylamine. Picture the complete balanced reaction scheme on screen with structures of acetamide and ethylamine clearly labeled, along with the mole numbers next to each reactant and product. This example illustrates how the Hoffmann bromamide reaction is a practical tool for efficiently making primary amines with predictable yields. Alright, future chemists, let's wrap up our amine preparation journey. We've seen that nitro compounds can be reduced with hydrogen and nickel catalyst to form amines. Nitriles can be transformed into primary amines using lithium aluminium hydride. The Hoffmann bromamide reaction shows us how to convert amides to amines with bromine and sodium hydroxide, and finally, Gabriel's synthesis cleverly uses potassium phthalimide and hydrolysis to yield pure primary amines from alkyl halides. Each method has its own charm and application, helping chemists build the amines that color our clothes, make medicines, and create countless useful chemicals. That's it for today's concept. Remember, chemistry is all about transforming simple things into amazing molecules. Keep smiling and see you in the next session.